Today, we want to continue solving equations by reading the expression, then performing inverse operations in reverse order. We'll notice that, excuse me, most of our big rule is the first one. The inverse of an exponent is a reciprocal exponent. The other rules have to do with us reading the expressions through the exponents, in that we incorporate radicals into our equations by reading radicals as fraction exponents. We can incorporate variables in the denominator as expressions with negative exponents. The extra thing that we have to remember is that equations with even numerator exponents can have 2 or 0 real solutions. So this is what, when I first introduced this rule, I was just going with the 2 because I had a mind to switch out this real solutions business, but I want to emphasize this 0 so that we're looking at something other than real solutions. Also, statements are harder to remember the more ors they have. The more exceptions that you have to put into things, the harder it is to remember. So I just lead with the 2 real solutions when there's an even numerator exponent. But this is what we want to look at today. The 2 or 0 real solutions thing. So today we want to look at the 2 or 0 real solutions thing. So what we want to focus on is an equation where the exponent has an even numerator. So it really comes down to 2 equations. X squared equals 9. We know that there are going to be 2 solutions. We can get at them by raising the 9 to the 1/2 power. But when we see the even numerator exponent, in the equation, we just want to notice this as there are going to be 2 or 0 real solutions. So this is where we'll have 2 or 0 real solutions. We just have to notice this. When we go about solving, we do the same thing that we always do. We solve by performing inverse operations in reverse order. So we'll take the 9 and raise it to the inverse of a square, which is a 1/2 power, and come up with 3. Since we got 1 real solution, we'll have the other real solution. So we get 3 and we get -3. We can also read the 1/2 power as a square root. So we could have also solved this by saying x equals the square roots of 9, which is going to give us a 3 and a -3. There's some nuance here. When I write the symbol square root of 9, we usually mean we're talking about the principal square root, the positive one. And so if someone asks you what the square root of 9 is, you just say 3. But we're solving an equation, which is find all the x that fit this description up here. And there are 2 values of x that fit that description, 3 and -3. So when we talk about the square root of 9, we're specifically talking about the positive square root of 9. That's how you should interpret that symbol. The plus and minus shows up specifically because we're solving an equation. That's just being super pedantic. But you shouldn't, if you're writing some screenplay somewhere, you shouldn't hinge a scene on or -3 unless you're in the context of solving an equation. That's all. So The other thing, the zero solution comes up when we have, say, x squared is equal to, let's say, -9. In this case, we see an even numerator exponent. We see an even numerator exponent in the equation. So therefore, we should expect to see 2 or 0 real solutions. Now, if we just follow our nose through the things, we'll say x squared is equal to -9 to the 1/2 power. And we might not have noticed yet, but when we try to punch this into our calculating machine, if I try to punch or press, I don't have to be so forceful about it. If I try to raise -9 to the 1/2 power, then I get an error for non-real answers if my calculator is in real mode. And here it's saying the calculator's in real mode. Right now, my calculator is set to keep it real. So in this case, we get non-real answer from our calculator. And it seems like an emergency because our calculator is saying this in all caps. Even though the calculator is capable of writing lowercase letters, it's like all caps, so it's shouting at us that there are non-real answers. It's like, non-real answers. It's like, oh, calm down. It's a thing, calculator, but it's an emergency. I don't know why it's such an emergency. So this is the case where we have no real solutions. And notice that we don't say no solutions, we say no real solutions. When we go back and look at the equation itself and think about what even exponents do, we can see that we're not going to have any real numbers that fit the bill. Because we're raising if we raise a real number to an even power, I'm either going to have 2 positives or 2 negatives. If I have the same sign, I'm always going to end up positive. So it makes sense that there are no real solutions. Oops, I need 2 of them now. It makes sense that we'll have no real solutions because if I have a positive times a positive, I will get a positive. If I have a negative times a negative, that will also be positive. And if we're squaring something, they're going to have the same sign. When we square the x's have to have the same sign. Because it says write 2 copies of the thing what's being squared. So when we square the x, we're writing 2 copies of the thing that includes the sign. That's why we needed the parentheses around the -9 squared, or to the 1/2 power. We get no real solutions. So this is how we're going to base our decision. If we're looking at a square, and a square is equal to a negative or an even exponent, if we see an even exponent in the equation and it's equal to a negative number, then we know we're going to have no real solutions. At this point in our equation solving history, we're just going to write no real solutions, but it does raise the question, if they aren't real solutions, what are they? Which is a fair question to ask. So there are no real solutions, but there are complex solutions. And the complex solutions involve the square root of -1. They involve imaginary numbers. Imaginary or imaginary? Hey Siri, how do you spell imaginary?
Imaginary.
Oh, it is A-R-Y. This is one of those words that never looks spelled, looks always wrong to me. Imaginary, I just looked it up. So it's A-R-Y, but it looks wrong. But if I put an E-R-Y, that looks wrong as well. And I don't know what's wrong with my mind, what's wrong with my brain that I can't look at this word and say that is spelled correctly. It just looks wrong. I mean, logically, I know it's spelled correctly, mainly because Siri just told me that that's right. But are you sure? Because that looks wrong. Who knows? The human mind is a weird, weird thing. So that's the point that I want to make today. I started off as calling out even numerators, as you'll have two real solutions, but it could be 2 or 0 real solutions. The level below the level above this is that or below, I don't know, next to. The next level would be looking for the complex solutions to our equations. That'll involve imaginary numbers, which are multiples of the imaginary unit, where I is the square root of -1. So clearly this is not a real number, because it has the property such that when you square it, we end up with -1. So I is clearly not a real number, and so we call this the imaginary unit. So the imaginary unit is the square root of -1. It's the unit that we made up when we said, when we saw these squares coming up to negative numbers. Say, well, no real number will do this. Let's make one up. And then who knew how useful they were going to be when we invented? We, like I was there. So, because I don't want to make things too complicated at this point. That's why we're going to stop and say there's no real solutions. Let's look for the real solutions to our equations. So if we see an even numerator exponent in the equation and a negative number on the other side, we're going to just declare no real solutions and be done with it. And then worry about the complex solutions when we start looking at graphs of quadratic functions later on. And then you'll learn about how far it goes. So whatever the exponent is, that's how many complex solutions you're going to get. So we have to get into trig to look at that. But looking into your future trigonometry, whatever the exponent is, that tells you how many solutions you're going to get. So in future, if you have x to the n, where n is some integer, positive integer, equals some constant, has n solutions. But the solutions might be complex. So even if you have something like x cubed equals 8, our only real solution is 2, but there have to be 2 other ones that happen to be complex. So that's one level past once we learn the imaginary unit. Any questions? So the other key thing that we want to point out is that this 2 or 0 real solutions is based on the numerator of the exponent. So let's make sure that we make that distinction. So for example, if I have some fraction exponent, so if I have x to the 2/3 is equal to 5, I see that the numerator of the exponent is even, And so I could have 2 or 0 real solutions. Since the 5 is positive, we're going to have 2 real solutions. So it's the numerator, the 2, even numerator exponents in the equation. That tells us that we're expecting 2 or 0 solutions. Since the 5 is positive, we'll get 2. So there's an even numerator exponent in the equation. The 5 is positive, so there will be 2 real solutions. If we break our equation down and it comes down to this, x to the 2/3 is equal to -5. Once again, we key on this even exponent up here, or the even numerator, and we see an even numerator exponent in the equation. But we see that the 5 is negative. We can't raise something to an even numerator exponent and come up with a negative, so therefore we have no real solutions. We want to make sure that we're looking at the equation and singling out the numerator. So for example, if I have an x, if my exponent is the other way around, say 3/2 equals even a -5, the numerator of the exponent is odd. So here we see an odd numerator exponent. In the equation. So now I don't have to worry about the 2 or 0. We will have 1 real solution. Just proceed normally. Take the -5 and raise it to the reciprocal exponent, 2/3. -5 to the 2/3. 2.924. So if the numerator of the exponent in the equation is odd, just 1 real solution, everything is just fine. Odd numerator exponents respect negatives. They just make things negative. Even numerator exponents try to make everything or successfully make everything positive. Even numerator the exponents are your friends that are like, oh, dude, just cheer up when you're sad. And that's just not how things work. They're disrespecting your sadness. Don't let them get away with that. Any questions? Last thing I want to point out today is when I say even numerator exponent, I'm just not stopping there. I'm saying there's an even numerator exponent in the equation. Because notice that here we see an even numerator exponent, but it's not in our original equation. So that's why I'm calling out specifically the even numerator exponents in the equations. And the reason I keep referring to even numerator exponents in the equations is that I want us to read things with exponents as much as possible. So I want to be able to look at an equation that says, let's say 5 over the square root of x cubed plus 1. Oops, this is not the example that I wanted us to think about. That's the other example. So if I have the 5 over the square root of x minus 1 all cubed is equal to 7, I want us to be able to read this equation, or read the expression, as x minus 1 to the negative 3 halves. So there's a lot that goes in there, but we want to read this expression as 5 times x minus 1 to the negative 3 halves. The reason that we can do that is we read the order of operations on the expression itself. And the first thing that happens is we subtract 1, then we raise to the third power, and then we do a square root, which is a 1/2 power. So we have consecutive exponent operations. And fourth, we multiply by 5. So because we have consecutive exponent operations, we can combine them into one operation, to the 3 halves. We want to make sure that we combine our consecutive exponent operations. We also notice that things are being raised to the negative 3 halves, since the 5 is being divided by this square root. So I should have called out one of these exponents as being negative. So just remember, combine consecutive exponent operations. CCE, oh, that's terrible. Don't just abbreviate things. When you're working at a school for a very long time, you just start to use abbreviations for everything. If things have a very long name, you just take the first letter of each thing and then you start doing like in Marvel with Shield, where you come up with a name because you want it to spell shield. You don't come up with a name and say, oh, look, notice that all the letters spell out shield. How convenient. No, you specifically wanted the letters to spell out shield. Anyway, it's kind of like I've been on a committee and we wanted the committee to spell a certain thing. Because what we were calling the committee is like, well, if we call it this, then it doesn't spell a word. So we rearranged things so that it did spell a word. It's like, well, this is what we're going to call our committee. Because we had this specific goal in mind to make sure it spelled something. That's just human nature, but you get a lot of it when you're working in a school. Any questions? Not about the abbreviation thing, about the exponent things. Taking a step back from the work we've been doing this last week on the solving equations by performing inverse operations in reverse order, we're covering a lot of ground because we're focused on one kind of equation where the variable appears only once in the expression. But by restricting ourselves to one instance of the exponents, we gain a lot of power because we can express a lot of different kinds of equations in terms of exponents. Then we only have 3 things to worry about: addition, multiplication, and exponents. Once we learn to read expressions, we can perform inverse operations in reverse order, and we solve a lot of equations. So it's very useful. And then everything else, like the quadratic formula, we're going to solve the quadratic. Instead of using the quadratic formula, we're going to rewrite our ax squared plus bx plus c, for those of you who are more familiar with it, into one instance of the x, so that we could do inverse operations in reverse order. When we're solving radical equations, if there's more than one instance of the x, we want to rewrite it so that there's one instance of the x so that we can perform inverse operations in reverse order. Everything else is pretty much a niche equation. It gets blown out of proportion because we spend a lot of time doing those things. But if we wanted to solve this equation, I would take 7 and first invert the times 5 and divide by 5. And then I can combine this. This is all being raised to a negative 3/2 power because it's in the denominator. So I'll take the 1.4 and raise it to the the reciprocal, negative 2/3. And then I will add 1. Inverse operations in reverse order. So I get 1.799. Any questions? If I take the 1.799 and run it through all these operations, I should get back to 7. Let's find out. So first we'll take, oops, I wasn't showing you my operations. They're my operations. So I take this 1.799, I'll first subtract 1, and then I'll raise to the 3rd power. And then I'll take the square root of this number. And then I'll take 5 divided by this number. And it comes out 7, just like we suspected. All right, that's what I wanted to talk about today. Just the watch out for your even numerator exponents in your equations, because you could have 2 or 0 real solutions. It's not that much extra fancy stuff to worry about, because when you're trying to solve the equation, it's okay if you forget, because your calculator will tell you that things are going badly. Because you'll try to take an even root of a negative number, and your calculator will say, hold on, no real answer. So it's not really that much extra to remember, but we want to be aware that it's a thing that will happen, and it's not your calculator behaving badly. It's the fact that we can't raise real numbers to even exponents and come up with a negative number. Only imaginary numbers have that property. All right, that's going to do it for today. I will see you all on tomorrow. Have a good day, and thanks for playing.